This is an introductory tutorial for Anthroposcaper. Let's create a new drawing in the project tree and draw a rectangle. For the dimensions, we'll use precise input, the tab key, and typing a value. Move the camera with the middle mouse button. Rotate with the right button, and zoom with the wheel. Next, we'll draw a line and round off the corner. An arc, like any curve here, is actually made of straight segments, because in the end what we're after is a 3D mesh. Let's select the arc and change the number of segments. And you can enter not just a count, but the length of a single segment, say, 1 meter. Then the app works out for itself how many segments the arc's length needs. And now the interesting part. Let's switch to face selection mode. And you can see the closed regions between the lines already exist. You don't trace them. The app finds the faces from the intersections on its own. And when you edit the drawing, it updates them automatically. Let's prepare the materials. When we import a ready-made 3D model, the materials and textures come with it, inside the file. But for the faces of the drawing itself, you have to set up the material by hand. Let's keep this tidy. In the project tree, I create a separate folder for the library, and inside it a folder for materials, so the resources don't get mixed in with the drawings. From here, it's a simple chain of 3 links. First, the image, an ordinary texture file, grass and asphalt, say. On top of the image, you create a texture. That's already a project node, which references the file and holds its mapping settings. And on top of the texture, a material, the thing will ultimately assign to faces. Image texture material. So that's what I do for both surfaces. I add textures and point each one to its file, then create materials for them and link each to the right texture. The result, 2 finished materials, grass and asphalt, that now live in the project library. The materials are ready. Now let's define the classes. A class is a named set of attributes, which you then assign to elements of the drawing with a single tag. Classes aren't tied to a specific object. They're stored in a separate project entity, a dedicated tree node. I create this node and define the first class, grass. Its body has 2 attributes. The first, color, sets the face color in the editor. It's what highlights the region on the plan in topology display mode. The value is given in hexadecimal, 3 or 6 digits, with an alpha channel if needed. Here it's 0, A0, that is, green. The second attribute, material, defines the face's 3D material, which goes into the build and on into the export. I reference the matte grass I created earlier. Then, the same way, I add the class road. So color governs only the look on the plan, while material is responsible for the result in 3D. Back to the drawing. I turn on the DCL display. I switch to face selection mode and start handing out classes. I select the grass and type the tag grass. I select the roadway, road. Notice, the faces are colored right away, and the color comes from the color attribute of the class we applied. Now let's look at the 3D. I turn off the DCL display and hit build scene. The projection is controlled by an attribute, proj. I give the grass proj, planar 2010. That's a flat projection from above, and the 2 numbers are the size of 1 texture tile in meters, 20 meters along one axis and 10 along the other. I rebuild the scene. You can see how the texture cell stretched along U and V. You can also give just 1 number. Then the tile is square, and a single value works for both axes at once. To make the grass look realistic, I'll set a smaller size, 3. And I'll set the projection for the road too. Next, to make the road lower than the grass, I set the attribute DZ, minus 0.15. That's a relative height of 15 centimeters, which gets added to the height of the drawing's objects. I prepared the curve geometry ahead of time in an external editor. Here it's Blender. Anthroposcaper has no 3D modeling tools of its own. And that's deliberate. Complex meshes are easier to make in a specialized package you're used to. I've got two curb models here, a regular section and a low one. Let's export them. File, Export, and what we want here is GLTF 2.0. The format offers two options, GLB and GLTF. We need GLB specifically. The difference is fundamental. GLB is a single self-contained file with everything packed inside at once, geometry, materials, and textures. GLTF, on the other hand, keeps resources scattered as separate files alongside, and we don't support that. A couple more words on how a scene from Blender lands in our app on import. The split into separate meshes goes by the top level. Each object sitting at the root of the scene becomes a standalone mesh in our app, with its own name and its own insertion point. And anything nested inside such an object is, conversely, merged into a single mesh together with it. Now let's import this file into our app. I go to the library folder and start the GLB import. The app lays out the file's contents into components inside a single folder named after the file. Inside there are folders with resources, and each resource sits as a separate node. Everything that was packed into the GLB is now available as separate pieces of the project. Besides the broken-out resources, the import also creates an assembled scene. In it, both curbs are together, arranged exactly as they stood in the source file. We've reached the key mechanism, templates. A template describes what geometry to lay out and along which edges, and the system does it automatically. First, I'll prepare a small test scene right next to the imported curbs. This is a handy trick while setting things up. The source meshes and the build result end up in one place, so any change to the template shows up right away, with no switching around. On the faces of the test scene, I assign the classes, grass and road. Now the template itself. Its foundation is a closed contour split by an internal segment into two faces. I draw a rectangle, then run a segment through it, the edge along which the template will be tiled. Precision matters here, so I use coordinate input. The curb mesh is modeled from the origin and is 1 meter long, so I set the edge segment the same way, from 0, exactly 1 meter long. Then the geometry matches the template's axis 1-to-1, with no adjusting. Next, I set the correspondence of the sides. The two faces of the contour are the two neighbors of the future edge. To one face I assign grass, to the other road. By this I declare that the template applies to edges that have grass on one side and road on the other. What's left is to bind it all into one family. I set up a separate layer and put the tag T, curb on it, the template's name. Then I select the template's objects and move them onto this layer. The tag is inherited automatically, so both the contour faces and the curb meshes get marked as parts of the curb family all at once. There's no need to set the tag on each object by hand. The template is ready. I run the build, and the system goes over the test scene, finds the edge between road and grass, and lays the curb along it. From here, it's convenient to fine-tune the template on this same test scene, tweak, rebuild, see the result right away. We see a problem. On a right angle, the curb bends. It wraps around the corner as a single piece. Geometrically, it's correct, but in real life, it doesn't happen that way. At a corner, one curb usually ends, and another begins from it, butted right up against it. To understand why this happens, let me explain how a template is tiled by default. The system takes the whole chain of edges, works out how many whole copies of the template fit into its length, and lays them out as one continuous ribbon. To fit a whole number of templates, they're scaled slightly along their length. At the bends, this ribbon doesn't break. It just curves along the line, and each copy deforms at the turn. For flexible geometry like a fence, that's exactly what you want, but for a rigid curb, it isn't. You can mark a break by hand. I put the tag break on the corner vertex. After the rebuild, you can see, at this point the ribbon breaks. One copy honestly ends here, and the next one starts fresh from its own end. No more bending through the corner. But you don't have to place break on every corner by hand. This can be automated right in the template. I add the attribute break with the value 45 to its axis. Now the rule reads, break the ribbon at any bend sharper than 45 degrees. I rebuild, and all the sharp corners in the scene break on their own, while the gentle turns still go through as a single ribbon. Moving on to the rounded section. It has its own catch. The angles of a gentle arc are small, each bend far below our threshold of 45 degrees, so break doesn't trigger here, and rightly so. The ribbon should run along the arc as one piece. But it looks messy. The number of arc segments doesn't match the number of curbs. The copies fall out of step and bend unattractively, breaking in the middle. The reason is a mismatch between two subdivisions: how the arc is split into segments and how the ribbon is split into curb copies. Let's line them up. I go into the arc's properties and set the segment length, 1 meter, exactly as much as one curb takes. It's worth recalling the meaning of this field here. In the segment count, you can enter not just a count, but the length of a single segment in meters. Then the app computes the count itself from the curve's length. The longer the arc, the more segments at the same given length. I set 1 meter and get as many segments as there are meters in the arc. And now everything lines up. The segment length equals the curb length. So each straight segment of the arc gets exactly one copy. The curbs sit along the chord, 1 to 1, with no stretching and no bends inside a copy. The arc's subdivision and the template's layout are now in sync. Now I'll show a subtler technique: how to lower the grass in one spot flush with the asphalt, making a smooth descent. First, I prepare the geometry. I add a line that will bound the descent zone and place 2 points. The grass will be lowered between them. First, about how not to do it. The most obvious move is to take these points and lower them in height, changing the z-coordinate. But here's what happens. Everything that meets at a point drops along with it. A point is a shared topology vertex. It belongs to both the grass and the road at once, so the road obediently sinks along with the grass. That's not what we want. I return the points z back to 0. The right tool here is the dz attribute, made for exactly this. I select the segment between the points and put dz minus 0.15 grass on it. This is a local drop in height, addressed to a specific side of the edge. The number sets the offset and the word after it, the class it applies to. I named only grass, so only the grass side drops by 15 centimeters and the road stays put. I rebuild. The grass has neatly gone down, the road untouched. But a new problem has surfaced. The grass dropped, but the curb stayed hanging in the air at its old level. The curb's geometry knows nothing about our drop. Let's fix this with baseline. I select the curb mesh in the template and set baseline grass. By this I say, set the curb's height to the level of the neighboring grass face, whatever it may be. Now the curb goes down along with the grass and stands on the ground again. Almost done, but one small thing remains. In the lowered spot, the grass geometry pokes through the curb. The face rides onto the mesh. This is solved by pushing the face's contour away from the edge. I add offset 0.1 grass to the template's axis. The grass face shifts by 10 centimeters, freeing up room under the curb, and the overlap disappears. The same grammar as DZ, a number and a class. If you like, you can specify the shift for both sides at once. Now the joint is clean on all sides. One more touch, this time about lighting. Let's look closely at the spot where the descent meets the flat part of the grass. There's a sharp shading boundary there. A clear break in brightness at the edge. The geometry really does break at an angle here, and the shading of the two areas differs, hence the hard seam. You can smooth this without touching the geometry itself. I select the points on this edge and give them normal up. A forced vertical normal. Lighting is computed from normals, and now at these vertices the normal points straight up, and the computation smoothly stretches the shading across. I rebuild. The sharp boundary is gone, and in its place a soft gradient transition. The face stayed the same. Only the way it's lit has changed. I added a new class, road high. Its settings are the same as roads, but without the DZ attribute. That is, it's a road lying flush with the grass. And I added one more template between road high and grass. It's essentially a copy of our road grass curb. Only the sides are marked for the new pair of classes. Now the scene itself. Its peculiarity is that on the road slope section, there are several points in a row. Lowering them one by one, giving each its own DZ, is inconvenient. For cases like this, there's slope. I bound the slope zone with a segment to get a separate face and put the attribute slope, road high road on it. This means don't set the height inside the face by hand, but smoothly interpolate between the levels of the named neighbors, from the raised road high part down to the lowered road. I rebuild, and the road smoothly descends from one level to the other. Let me dwell on why two different curbs, the one along the lowered road and the one along the raised road, join with no seam. At the transition from one level to the other, they flow into each other as a single ribbon, as if it were one curb. And the reason is exactly one. Both templates carry the same family name, T, curb. The name is precisely what binds templates into one whole. The system lays geometry not along individual edges, but as a ribbon along a chain of connected edges, as long as they belong to one family. And which variant to place on a specific edge, for the lowered road or the raised one. It decides itself from the classes of that edge's faces. So at the boundary of levels, the ribbon doesn't break. Only the variant inside it changes. Let me show that it's the name that matters. I take the second template and change its family name to a different one. I rebuild, and the joint is gone. Now these are two different families, two independent ribbons. Each considers itself standalone, and at the transition honestly ends with its own cap, unaware of the neighbor. The curbs have stopped flowing into each other. Now, about template specialization. How to keep a general variant and a more specific one within a single family, and make the system pick the right one itself. Let me recall where we are. The curb for the raised road, road high grass, we made as a copy of the lowered road curb. That is, tall. We did that with one goal, so the curb would be visible on the descent. But that's essentially a patch. Where the road runs flush with the grass, a tall curb isn't needed. A low one is called for in that case. And a tall one is appropriate exactly on the descent at the transition of levels. So we need two variants in one family. First, I make the proper road high grass template with a low curb. This is the general case. It applies everywhere the raised road borders the grass. Now the tall curb should trigger not everywhere, but only on the descent. For that I refine it. I add the tag slope to the road high face of the template. By this I narrow the condition. This variant fits not just any road high grass edge, but only one whose roadside is specifically a slope, marked slope. From here a simple rule works. When several variants of the family fit an edge, the more specific one wins, the one that matched by the greater number of features. On the ordinary flat part, the road high face has no slope tag, so only the low curb fits, and it's the one that stands. But on the descent, the face carries slope, both fit it, but the tall one is described more precisely, and it's the one that wins. Meanwhile, the family name is common to both, so the transition stays seamless. It's still the same single ribbon, just with different variants on different sections. Now let's add railings. I've already prepared the template and the test scene ahead of time. The task is this. The railings should appear between the road and the grass, not everywhere, but only where the drawing's line is marked with the tag rail. The mechanics are exactly the same as we saw with specialization, only now the selection goes not by face, but by the specific edge. I refine the template. I add the tag rail to its axis. By this I say, apply only to edges that have the same tag. And on the drawing itself, I put rail on the segment along which I want the railings. I build the scene and discover something unexpected. The curb on this section has disappeared. The reason is competition. By default, each edge goes to only one family. Our railings and the curb both lay claim to the same edges between road and grass, and where the tag rail sits, the railings are described more precisely. They win the edge and push the curb out. But we need both at once. For this, there's the tag overlay. I put it on the railings family, and it stops competing for the edge and simply draws on top. I rebuild. The curb is back, and the railings stand over it. Next, about size and distribution. I add the attribute N1 to the railings axis. In short, N sets the exact number of template copies on the edge. 1 means a single copy across the whole span. You can see how all the geometry stretched proportionally to the edge's length. But that won't do. The posts should be their normal size, not stretched along with the section. Here snap helps. A mesh marked with it doesn't stretch. Instead, it's pinned by its anchor point to the start, the end, or the middle of the segment. I deliberately split the railing model into several separate meshes, the posts, the regular railing section, and the central section, and I assigned each its own anchor. The posts snap, begin, and end. The regular section just snap, pin to the nearest edge, and the central part snap center, so it sits exactly in the middle. Now let's turn our attention to the corners. There the geometry distorts. The copies deform at the turn. For some things that's exactly what you want. A curb, for instance, should follow the bend. But railings shouldn't bend, they're rigid. I add the tag rigid, and the copies stop deforming, keeping their shape at any angle. Now everything's as it should be. And one last touch. I'll move the railings deeper into the grass. The mesh's base point, its origin, matters here. It's relative to it that the mesh is seated on the template's axis. In our case, the base point is at the center of the mesh, and as I shift the railing model, it moves along with the base point. And here I see a new problem. At the end of the span, the railing's cap reaches the edge of the road and rides onto the curb. The point where the mesh reaches the edge is computed by exactly that base point of the mesh. This is controlled by the attribute cap. It sets how far the mesh's end reaches at the boundary. I set cap, normal, or cap by sector. In the first case, the end is cut along the normal to the edge. In the second, along the bisector of the joint. The railing's end sits exactly on the boundary and no longer rides onto the curb. Right now, the railing template has 2 posts, one at the start of the section, another at the end. As long as there's a single section, all is well. But when the copies line up in a row, the end of one copy meets the start of the next, and at each joint 2 posts stand at once. Duplicates appear. This is cured with rolls. A template can have not only a regular, repeating piece, but also special ones, a start and an end, which are placed once each at the ends of the whole ribbon. Let's use that. I'll split the railings into 2 templates of one family. The first, the regular section, it's tiled across the whole length. The second I mark with the roll tr end. It's the end section. It'll stand exactly once at the very end. Now I remove the second post from the regular section, leaving only one at the start. The logic comes out like this. Each regular copy brings 1 post at its start, so at the joints between copies there's always 1 post, no duplicates. And the very last edge, where there's no regular section anymore, is closed off by the end template. It's the one that places the final post. I rebuild. The posts go at an even pitch, 1 per joint, and there are no more duplicates. Let's add some flexibility. So as not to set the tag rail on a multitude of edges, let's make 2 more sets of templates. We remove the tag rail from the axis edge, and instead add it to the road face in one set, and to the grass face in the other. Now you can put rail on a single road region and railings will appear all along it. Or on separate grass regions adjoining the road. That is, minimum markup and maximum geometry. Right now there's an inconvenience. The number of templates multiplies, and they all have to be copied. But we'll definitely do something about that in the future. Let's move to a new scene. Here we have a mesh fence with brick columns. On it, we'll cover two things: texture tiling and rotation along the bisector. Let's start with the texture. Look at the short fence span. It's noticeably narrower than one template. And the chain link mesh on it looks unnatural. The texture squeezed, the cell stretched along with the geometry. The reason is that by default the texture is stretched across the whole mesh and deforms along with it. The netting is a separate mesh, and it's the one we need to work with. But it's inconvenient to select. Another mesh lies on top and blocks the click. Here object hiding, which lives only in the current session, comes in handy. With the H key I hide the mesh that's in the way, and now the netting is easy to reach. By the way, there's also the I key nearby. It does the opposite. It isolates the selection, hiding everything else, and shift with these keys brings the hidden back. I select the netting mesh and put UV tile on it. This switches the texture's behavior. Instead of stretching across the whole length, it starts to repeat, to tile, at its natural scale. I bring the hidden mesh back with Shift, H and rebuild. Now the netting cell keeps the right size and doesn't distort. The texture repeats in the positive direction of the U texture coordinate axis, along the ribbon. Second, the columns at the turns. Notice, at a bin the column looks along one of the sections, rather than splitting the angle in half, and the joint looks crooked. To make the column rotate along the bisector of the joint, I put the tag bisector. It got better. On gentle angles the column fits neatly into the turn. But on sharp, right angles of 90 degrees, it looks bad. So I limit the condition. I write bisector, less than 80. Now rotation along the bisector applies only to bends softer than 80 degrees, while sharp angles the column passes straight, without tipping over. I rebuild. On gentle turns the columns follow the bisector. On sharp ones they stand straight. One more scene. Now with barriers. On it we'll cover the case where you just need to string geometry along a line without cutting the plan into faces. I've got two barrier templates prepared. They're built as sparingly as can be. Nothing hangs on the meshes themselves, and on the template's axis there's a single tag, rigid. And here it's worth clarifying the difference, because rigid can be placed in two spots. Rigid on the axis makes each copy of the template rigid as a whole. The copies don't deform, hold a fixed length, and don't bend along the line. And rigid on a single mesh can bend along the path, but tries to hold its shape and doesn't skew. The second template I want to mix in every other one. For that I put every 2 on the template's layer. This barrier will stand not at every position, but at every second one. Now an important point. The line the barriers run along lies right in the plan, and, by its intersections, cuts the drawing into extra faces that gets in our way. To make the line take part in the layout but not affect the topology, I put the tag node cell on its layer. It excludes the layer from face building. You can also put this tag right on the object. It's useful to understand which way the ribbon is built. I turn on the point display mode and see an arrow. It shows the direction along which the geometry is laid out. The direction is set by the order of the line's vertices, and it can be reversed. In the Polylines properties, there's a reverse button. I toggle it, and the arrow, and with it the whole layout, go the other way. Finally, about the insertion step. I change every to 3. Now the second barrier appears every 2 positions, less often. And if the copies aren't rigid, the step can be given not in counts, but right in meters. Every in a number with the letter M. An insertion every so many meters, regardless of the template's length. And last, let's run through what stayed off screen, but is worth knowing. I'll start with saving. I'll open the Save As dialog. The main thing to understand here about your data, it stays with you. The app runs entirely in the browser, and nothing goes to a server, not projects, not imported files, not the build result. By default, a project is stored in the browser itself, in its local storage. But you can't rely on that as a safe place. Clearing the site's data, incognito mode, a different browser, or a reinstall, and the storage is gone. So save anything you value to disk as a separate project file. That's the truly reliable copy, and it's worth making regularly. Now about output. There are 3 export buttons on the panel. Export 3D gives out the assembled three-dimensional scene as a GLB file, with all the meshes, materials, and textures. It can be opened in Blender, 3ds Max, or any package that works with GLTF. Export to DXF outputs the flat drawing, the plan's lines themselves, into an interchange format for other CAD apps. And export faces to DXF saves to DXF the recognized closed topology face regions rather than the source lines. A couple of words about view navigation. It speeds up the work a lot. The keys T, F, and L set the standard views, top, front, and left, and by the active coordinate system at that. And P and O switch the projection P, perspective, O, orthographic. The full list of hotkeys is in the documentation. If some keys don't work, most likely the viewport has lost input focus. The simplest fix, click on it with the middle mouse button. When focus is active, a faint white frame is visible. I go back to the site via the house button and open the documentation section. It has a detailed guide, and at the very end, in the reference, there are two especially useful tables, the full list of hotkeys and a summary of all attributes, the very tags we worked with throughout the video. Keep it handy until you've memorized it. That's all. We've come the whole way, from an empty project and the first lines, through topology, classes, and materials, to templates, and assembled a finished 3D scene. Thanks for making it to the end. Just don't forget, this is an early and not the most stable version. Save often. I really need your feedback and support. All the links are in the description.